Wait, sorry. Okay.
So, as I said, here we are going to talk a bit about the theory, then we'll see an application case of a fragment binding to a protein, and then we'll try to do all together some exercises and get along with the commands. So, the theory. Well, as I said, many of you are probably aware, but it's in the field of, or in the context of HCMD, it's a big application, because usually we are interested to see what's the affinity and what are the rates between a drug and its receptor. So why is this important? So in the cell, everything is made out of interactions, and if we want to block a receptor because of a disease, or if we want to properly understand how it interacts with a drug or another molecule, the first step is to see what are the interactions between the two partners, and then try to see the affinity, and we can then improve them or better design these interactions and modify them. So the first step is always try to get the affinity and the potency, especially if we are in the context of drug discovery. Try to, for a series of compounds, try to see which are the most potent ones and keep improving them. Also, it's becoming a hot topic, try to understand what are the kinetics of binding, because it's very often in the device scenario we are under non-equilibrium conditions, and then the kinetic and the residence time especially plays a key role. So it's also becoming very important, especially in pharma companies, to understand how a drug which is already in the phase 1 and 2, how it properly binds the rates to its receptor, and see if we can also modify them. And so for this reason, actually understanding the thermodynamic and kinetic interaction of a drug to its receptor or of a series of fragments, if from a first stage of the drug discovery pipeline, then we could go forward and improve many of the following compounds. So I will go first for theoretical description. When we have a drug and its receptor, it usually binds with with a K-ion, with an on rate. This on rate is dependent on the concentration of the drug. This means also it's dependent on the dose, and it unbinds with a specific K-off. So we can try to compute this K-ion and K-off, and these kinetic parameters are also related with later with the thermodynamic parameter. So once this reaction has been formed, so we have in equilibrium the drug and the receptor, the proportions of the concentration between them in equilibrium gives the KT. And like the smaller is the KT, then the most potent the compound is, and we can also relate it to the K-ion and K-off, so that's why kinetics and thermodynamics are interconnected. We can tune any of the three parameters, and then the others will be involved. If we try to see it in a picture, here we have in the initial state is the drug and the receptor. Imagine the drug in solution and then the receptor, and in the final state is the drug already bounding the receptor. This is a very simplistic model, very simplistic mechanism, because it has only one step, and then it's already bound in one single pose. So like it's very simple, because in the current model view, the drug can have many poses, and also the protein can have many conformations. But going in this simple example, the affinity of the compound, it's only the difference between the initial and the end states, while the rates are the difference, or like the energy are related to the energy difference between the initial and end states to the transition states, which is like the point of maximum energy. So we can tune the shape of the energy barrier, and then we will be tuning the kinetics without affecting the KT, or if we change the end or final states, we can actually change the KT, but we will also be affecting kinetics. Yes? No? Okay. Of course, this is a very simple mechanism, because it only goes through one transition state, no metatransition states or intermediate states in the pathway. And there are many other complex mechanisms of binding. I'm here showing only 3 of them. The first one is the first we've seen here. So from the starting point unbound to bound, without any conformational change or without going through any intermediates in the pathway. The second mechanism, it's called induced fit, and in this mechanism, the protein is a specific conformation in solution, and then when the ligand approaches, then it first forms a complex, and then it's followed by a second step in which the ligand and the protein adopt to each other and form the final complex. And in the third mechanism is called conformational selection, and in this case we have that the protein is alone in the apoform. It's has different populations for each of the conformers. This means that the ligand can have different affinities for each of the conformers. So if the ligand is alone in the system, then it can bind preferably to the second part of the protein, but maybe this is the lowest populated one. And then the equilibrium will shift to the drug bound, and then the population of the protein will shift towards the most affine protein one. And this is one, like the 3 mechanisms that we have currently today, but summarized in a very simplistic way. Well, we can see that actually there is no such a thing that one ligand binds to a protein with one specific mechanism, but instead there is a coexistence of all of them. So we can have the picture where of a conformational plasticity of the protein. The protein can have many different conformers in solution, with interconverting in them with very slow timescales, and then the ligand can bind with different affinities to each of them, and then in any of them perform a induced fit or shift the conformational selection towards one of them. And this whole picture, it's very important to be understood before the drug discovery process, and it's very hard to see experimentally because of the timescales of the processes. This is the point in which we can do critical information. We can see the populations of the protein before and after binding, and we can see the affinities of each of the conformers for our ligand. So here's what we can see. We can do critical information that experimentalists cannot. So we are going to see one very simple example. It's basically, we are going to analyze like a first step model. We are going to analyze the binding of one small fragment. Is very similar to benzamidine, to a protein called endothiapepsin, and we are doing the single mechanism, the single step mechanism that I showed before, the first one. So in this case, let's go a bit into the theory. Do you have access? Perfect.
So which session is that?
It's 7. Ligand binding. Here I'm just basically globing what we have in this folder. There's just a set of filtered trajectories. We have 20 different trajectories, and then choose the parameter, the topology, and the PDB file. Okay? Then, with these trajectories, I'm going to show you how does the protein look like. If I can. Okay, so you see, it looks like a dimer, but this protein in eukaryotes evolves to be a monomer, and then you have the ligand. If I end up typing these guess bonds false, it's because we want to read the correct topology from the topology file. You see, in this case, it's bound, but in our trajectories, we were starting from the ligand from unbound, and then leaving it for you to identify the pocket by itself. Okay. Okay, so now that I've shown you the filter files that we have 20 trajectories, and we need to create a map of these trajectories. So we need to see for each of the frames of the trajectories, where is the ligand, the fragment regarding in respect to the protein. So what we do here, usually for ligand binding, we usually do contact maps. This means that we take all the atoms in the ligand and we map it against the protein with a cutoff of 8 angstroms. But we could also do distances. We will wanna try this later, or we can try more fancy metric. In this situation, we are gonna try to do a contact map of all the atoms. Well, first we need to do a list, of the trajectories that we have. Of the trajectories that we have in our folder. Every simulation list needs to be related to a PDB. In this case, because we filtered previously all the trajectories, all the trajectories are related to the same PDB file. Okay, and now we go to we have many trajectories with different number of atoms, then we call alternative, use this command. Now we do the metrification that I was mentioning before. Now we have our trajectory list, and we can do the contact maps that I mentioned of all the ligand atoms against the protein atoms. I'm using the carbon alpha of the proteins, but you could also choose all atoms and change the cutoff of your ligand against. So if you run it, this. Yeah.
They can see it.
Just go here and present it. Bring it on like down.
Okay. So the ligand it's called mole, as you see, and then the first selection are all the carbon atoms in the protein. This is basically a BMD selection, an atom select. The last parameter that you have there, skip 10. This command is basically just reading one frame out of 10, because we have a lot of data and this will take 10 or 20 minutes to do now, but we are sort of filtering the frames and only looking at one out of 10.
How can I stop this started? Because of that, I don't have this filter, the skip in there. So.
Don't you?
No, it's not in there.
This is stop button.
From the top. Stop. There you go.
Press it.
Okay. Working so far?
Yeah, so it's
This usually takes a while, but if we are running usually in adaptive, then our simulation datasets are smaller and we can do this in a few minutes. In the past, when we have millisecond simulation datasets, this could take hours. In this case, I guess it's already running your computers. Can take like 1 minute.
Also, there is actually a progress bar here, but there is a problem with the notebook. We're trying to solve it with a Jupyter notebook. So it only shows you the progress at the end when it has completed. But we cannot do anything about it, so we are waiting for the response.
Now, here we can do some manipulation of the data we have. So now we have in our data for each, as I said, for each frame in the trajectory, it's converted to a contact map of the ligand against the protein, a binary contact map, and we can see how many frames we have. We have this number of frames, and given that we were skipping them, this means that we have 16 microseconds. We can plot our trajectories, and here, now because I dropped it, you could see that before I have 20. But because some of them didn't have the same length, I cut them all to have the same length, and then now they are 14 trajectories of 90 nanoseconds, more or less. It's not much, but actually a comment on the timescales of the simulations. These simulations were done with in brute force, so we weren't running adaptive or anything on them. So all of them were starting from bulk and then freely moved to identify the pose. So as a guess for the simulation length that you need to run, you can always, if you have a guess on the on rate, you can always compute with the concentration that you have, and then this gives you the amount of time that you need for one binding event. For instance, if it's a K-on of 10 to the 8, and then you have a usual concentration of 3 millimolar, you might need like 20 microseconds or something like that. If it's faster, then you need less, and then if it's a very slow K-on, about 10 to the 6, and then with the same concentration, you will need to run 500 or 600 microseconds. This is interesting because if you have a very slow drop and then you're trying to bind it, maybe you don't see any binding event, but because you haven't reached the time scale. So for a normal usual draft in the market with a K-on of 10 to the 5, we will need more than 1 millisecond if we do brute force. That's why the adaptive is useful, and also that's why here in this example with brute force we are using a very fast fragment of K-on of 10 to the 8 and to the 9. For this binding event, we need like less than 20 microseconds, and we have 16 as you saw here. So we can sample a few. One out of. And then Zika. So once we have this projection, these contact maps, we do a dimensionality reduction. Maybe you're aware of PCA, but this is sort of a similar thing in the sense that it's also doing a dimensionality reduction, but it's doing it against the slowest processes. So it's kind of, instead of having tons of contact maps, we are reducing it to 3 or 4 dimensions, which are varying the slowest processes. Okay, more or less. We've had questions. Frank is around later on. We can ask because it's a very theoretical problem. So it's basically done with this command here. Here we are looking at the dimensions. In this Zika project, we choose the number of dimensions we want to project our data in. We choose 3 because we don't have that much data. The number that you choose is kind of arbitrary. We usually go for 3 to 5, 10 if it's a very complex system, but 3 as a first guess usually works. I remember at the group in Frank, they were saying that they try with 1, and if it sort of works, they go for it, and then 2 or 3 you can go trying, and then from 1 to 5. You usually get a good approximation. It usually doesn't vary much. And this is the autocorrelation lag time, the number 2. I believe it's 2 nanoseconds if we choose, and we don't usually change that much. This command takes a while. Can I stop it?
It's kind of a question. I mean, it's 0 something. So.
Yeah, in this one you can see progress bars. Is it running right? Yeah.
I understand the 3 was the number of projected dimensions. What was the 20 that you changed it to?
It's the well, it's usually 2 nanoseconds. 20 was before because we didn't do a skip 10, so that means 20 frames. It's the autocorrelation lag time.
Okay.
Which I guess is like you're jumping in when you do the variances.
So
Is it running for all of you guys? Okay. If you were very interested in the theory of Zika, there are a few papers. It's very mathematical, but There are a few publications in the Frank Noe group. He's, I don't know if he's around. He's coming to the workshop, and it explains how it's the most optimal way to actually discrete to project your data into the slowest orders for biological scientists. Yes?
Description of states of the ground resonance.
Sorry, I don't hear you.
Could you please explain briefly the states of the ground resonance?
Optica. So it's basically
All resonance which you have, because in application it's clear, but states of
Yeah, so as I said before, we have our set of trajectories, and each of the trajectories has a ligand and a protein. Okay, so what we do, because that data is huge for each frame, we do the contact maps of the ligand against the protein. This means that if the ligand is here, then it has zero contact maps with the protein. We do this for each frame and for each trajectory. If we have 20 trajectories and 100 frames for each, then this means in the end we have 2,000 total of frames with contact maps. Then, because this data is huge, we maybe need to project it in something. We need to use a projection method like PCA or TICA. So you can think about TICA like a PCA projection method. It's basically a dimensionality reduction method, but in which doing an orthogonal projection into the along the most variant, along it was like the most, I don't remember PCA, but like the projection that are very most, then TICA uses the lowest dimensions in your system. So sort of like you can cluster your contacts and into wells and put more clusters into the metastable states. Okay, so and then after this, now you have the dimensionality reduction. You can cluster your data with geometry, and from this geometry, then we will build the transition matrix. I don't know if you follow me. After this, first we still have to cluster, and then build the transition matrix. So this is only like a dimensionality reduction of our huge data of contact maps into the slowest order parameters of our set.
Excuse me, and in this case you start all simulations with the ligand in the bound.
No, all the simulations have the ligand outside, so initially the contacts were zero, and then it freely moves until the pocket, till it identifies the pocket or allosteric sites or metastable poses. It freely moves, and we didn't do adaptive for anything, it's brute force.
Okay, so you don't guide your ligand into the bound.
No, it's totally unbiased.
But would that ligand is outside the protein, it takes a very, very, very long time to get in there, doesn't it?
It's inefficient in some way. It's a very fast ligand because it's a ligand that binds in 20 microseconds, but it's inefficient in the way that we are not learning from previous simulations. That's why the adaptive is useful. Because from each small batch, you start from bulk, but then in the following epoch, you start already from some learned states, and then you can follow on, and then you can reduce your data for one order or two orders of magnitude.
Sorry, I wanted to mention something. In this command that you have drop trudge, this command up there, in your case it says multiple 350, right? So if you did the skip 10 at the beginning, change this 350 to 35, otherwise it will drop all of the trajectories. And you will not have any trajectories left for the analysis afterwards. That was 350, and if we change the lag, then...
Sorry, change it to 35.
So inside this command, the drop trudge, it says multiple 350. Yes. So if you added the skip 10 parameter at the beginning, you should change this 350 to 35.
Or nothing, no? Just delete it.
Yeah, or nothing. Or actually, remove the whole multiple line, actually. Remove the multiples, whatever. Just make it drop trudge, simple, without any arguments. Yeah, like here, actually. So as in this example.
Excuse me.
Yeah.
I have a little questions about the TICO methods. You have mentioned that the difference between PCA and TICO is that TICA uses the projections of the slow degrees of the rotations of the system. But as I know, the principal components came from the covariance matrix in the PCA. In fact, equal to the normal modus came from the matrix of the Hessian. It's a relationship that the covariance matrix is the inverse Hessian matrix. So the normal modus, in fact, are the slow relaxation degree of the system. So if we put all the theory in trash now, what is the difference will be in the projections made by PCA and the TICA for the same systems?
So PCA
coordinates.
Yeah, PCA would project on the dimensions of the largest variance of your data, while TICA essentially calculates the time lag correlations of your variables, and then it finds kind of I think the ones that change slow, so the ones that have the highest autocorrelations.
But in fact, for this same system, if we make the two projections for the highest variance coordinates for the PCA and on the slow degrees of the rotations by the TICA, it will be the same projections, but with the high resolution. In case
no, it's kind of nearly the opposite, because the largest variance is usually the fastest process in your simulation. So if something, for example, in a protein, if you have a tail which is moving very fast, it will have a very high variance because it's moving all over the place. While if it's a slow process, in theory, it's not going to move much, so it will have a slow variance in space.
But from the same place, the large variance means a high collectivity of the process. You know, this collectivity it means there's a lot of atoms move in the same directions. There's no global motion.
Yeah. Okay, but there is no guarantee that this has anything to do with time, because PCA doesn't look at time at all. It's like an instant variance. So, well, I mean, if you want more technical details, you can ask Frank Novus coming later, and he knows everything about it because they developed it.
So. Personally, try to test it against my system because I haven't worked a lot with the PCA, and just interesting what's the difference in this method.
Yeah.
Because PCA works wrong in the big systems. Maybe this method will be more accurate.
So, okay, like in this example, which I typically show, the PCA would be kind of in the upper dimension, the largest PCA, while the TICA would be in the horizontal because the slowest process is jumping between the barrier of the two distributions.
It will show the entropy within the well, for instance, on the free energy surface.
Yes. So, yeah, the way I understand it essentially finds the largest barriers and then it projects your data along those barriers. And in the Markov models, if you put lots of clusters on the barriers, you get a finer discretization and it improves the quality of the Markov model. So that's the idea behind TICA. But as I said, if you want more technical details, Frank, they developed it, so they are the experts. You're welcome.
Okay, so after the TICA dimensionality reduction, so we have projected on the 3 dimensions, and now we need to cluster. It's so far it's a geometrical cluster. We can use k-means, k-centers. There are many clustering methods. In this case, we are using a mini-batch k-means clustering, and we'll do 1,000 clusters. The number of clusters is also arbitrary, but usually with 1,000, if we have a large set of data, it's fine. All those conformations which are clustered into which are less than 5 frames per clusters are then lumped to the neighbor clusters. But usually,
so, well, with what I did so far, I get this message number of samples smaller than number of clusters. Yeah.
okay, so here this is the command. We get all our data and we cluster it into 1,000 clusters using merge small 5. So now, if you remember from our set of huge contact maps, we are clustering them then by similarity, sort of like all those that were zeros because they were in bulk, we get into the same clusters. It's like a structural or geometrical clustering which still doesn't have kinetic information.
No, this one. Good.
Utilized cluster, it doesn't usually take much. So now, before we build the Markov model from this set of clusters, we have like 1,000 clusters, we need to choose the lag time at what we are doing the jumps. Usually we do this by plotting the implied timescales. The implied timescales are basically, there's a formula in which we see, let me show you. So for each of the lag time that we test, we build a transition matrix, and each transition matrix has its own eigenvectors. So the first eigenvector is always the transition, the probability equilibrium, as I mentioned yesterday, and then all the others are the slowest processes. Usually we are interested in fully combined with the two first slowest processes. So it would be this one, the first one in blue, and the other one in pink. And then the way to choose our lag time is trying to be Markovian. This means that the system has to be memoryless. So in order to do so, we need to choose a lag time for which the timescale has converged. We say then that the model has converged. Sometimes we need 100 nanoseconds to make the model converge. Sometimes it's a fast event that we need with 5 nanoseconds, like in Trip-Simple summiting, we have our model converge. It's system dependent, and it also means that if you can trust your model or not. So if you don't have a converged timescales, in this case it's not very good. If you don't have a converged timescales, you cannot trust much your model. You can also bootstrap your timescales with different extents of data to see if your timescale is actually converging or not. In this case, I would choose something like around here. It doesn't really matter because it's not really properly converged, but something around 200 nanoseconds, something here. And from a more qualitative point of view, this timescale is also giving you like the kinetic fingerprints of the system. So the timescale at which all the processes relapse. The first one is the slowest one, and we see in nanoseconds is 10 to the 3. So there is a relaxation time of 1,000 nanoseconds. This is more or less what the timescale is telling us. So in two parts, this is it. We decided to take, it doesn't really matter in this case. I think it's number 40. You can go 100, try different lag times. We're going to try later. Is it working for you guys? It's a
So basically, it just takes this and yeah, it's taking more well, did you I that's number. But all these commands are yeah, everything is based on.
Okay, so you might be getting by a mirror some view. Otherwise, it should look like something like this.
You probably have to provide the range, right?
The only x-axis is the lag time stored in the
This is what
values for the first agreement values. So it's actually the inverse of the timescale. The inverse of timescale. So the timescale also the slope.
You know these graphs that you come out with? get automatically.
So this is the sort of
No, it's like
It's not
Markov Model
like
testing.
we did analysis before. It is
So in Rayleigh, I'm doing the analysis of a graph. So this graph comes in, and I want to use it for computation.
Yes, just to see
How do I
conversions.
import it?
Oh, I didn't know
No, it's to choose a which one for you.
So if I have to, for example, if I'm going to that's computation, how do I export it out of this? No.
But I mean, yeah,
A disaster.
we'll be able to.
Yeah, sure.
No, I think we should have an option.
Wow, because this brings data block of it.
So really, the problem maybe is 500, so if you skip that, it has 350. Just 350 and choose.
No, but I think it is different because
I tried that.
It's working. Well, if you skip that, you project that they are not 500. So
no, because they were 5,000, frames. I already did the skip them thing.
so it uses some more.
Anyway, yeah, it's a PyMap problem that we are not aware of.
So this is a different version of the program itself.
So, no, it's actually the same version. It's probably the same.
Yeah, but she was very long to do it. Yeah, but it's kind of weird. Yeah, I don't know. You go to the next one, maybe tonight. If you want, you can go through that tutorial. It's on the HTML website, which works. The download Egyptian binding, which is on the HTML website. You can go through that and show how you want to explain the stuff. No, we have commented out the comments.
Okay, yeah, this is that.
You need to wait a bit. You need to wait and make the next progress bar now.
Okay.
It has a starter on the left, and it's still computing the same
Something.
Yeah.
Okay.
But there's no guarantee. Sometimes
Yeah,
the notebooks get stuck.
Okay, so
That's why I'm always.
But the macros, I've always been able to see them.
Yeah, but this no, it really just takes longer. You know, you might need to reduce the number of samples or something. So the model 1 that num samples 2 or something from the beginning. No. Before the command. No, before the command. Let's try this.
Model and sample too.
Yeah. So here model doesn't. Well, just to see if it's working. Doesn't want to visualize the viewer in GL. No, this is NGL. Ah, no, it's NGL has died up there. What? Oh, I don't know if this. Let's see. I think it probably reloaded the whole page. No? Oh, okay. Ah, okay, you can increase the number of samples again, shall I?
Okay. So after plotting your timescales, you usually choose the lag time, as I said, and then in the previous command, in Markov Model, you choose the lag time at which you want to build the transition matrix. And from this, you will get the equilibrium distribution and the slowest processes. We can also visualize how the microstates look like. So from this command, once we have our model, we can view its states. We choose 3 states. This is also, as I said, it's up to the user. Here we have our timescales, and then from this lag time, for instance, we want to see the slowest transition or the 2 slowest processes, so we choose then 3 macrostates. Then one to define the bulk and the other 2 to define the 2 slowest processes. How do they look like? That's the reason why I choose 3. The other look like very similar processing timescale terms, and this is how they look like. Maybe it's not a super converged system, and this is what happens when it's this is the pose, the one in orange, and then the others are not that. Sometimes this happens, sometimes you get a perfect model, sometimes. Then you might want to see the pose. You see, you might want there's a one random one here, but you might want to analyze what is the context of the pose is doing. This is important because it's like giving you the same sort of information as a crystal structure, but for your simulation. So if you think about it, at this point you have the energetics, the kinetics, and the pose of your slowest process. This would be like doing an NTC and then an SPR and then the crystal structure of your fragment simulation model. Okay.
So from this you get pose for all of the capital K and K1 and K.
Yes. So now we're gonna compute the rates, and for this pose and the others, we can see what's the delta T. If the system is converged and the timescales were perfect, then you can test the data and have some confidence in it. In this case, sometimes you need more data to sample more to have more statistics.
But you want to know the actual reality barrier.
Yes. We're gonna see that now. Not if you mean the transition states variable, no, we're gonna see the difference between the end and initial states, the delta G. So as I said, we can now calculate the rates. Now we have our Markov model. And I put it here. Maybe you don't see it. So this is what you were mentioning. It's a very like mild affinity fragment and upper millimolar fragment. This was macro, the macro was showing. If you see, that was the orange one. This one. It's macro number 2 here. And it has a very mild affinity of -2 kilocalmol. It's like non-binder, that's why it's also so fast binding. You see the MFPT on in nanoseconds. It's around 1 microsecond, which is very, very fast for a binding. And so imagine your scenario where you have a good inhibitor. You can see all the different poses it does along the pathway, and you can see the crystal pose in the end with its affinity, its kinetics, its on MFPT and off MFPT. So you can also compute K on, K off, and delta G at once. Is this what the delta G you were using?
Can you give us a realistic estimate of, if I look at the protein that's not so nice, not so fast, the binding event that's not so fast, how long do I have to calculate to get these numbers?
Okay, imagine you have when you can get a waste number, even if you haven't sampled enough, at least you will see some metastable states on the way. It's maybe not the crystal pose that you see in equilibriums, but you will see something. Imagine that you have a GPCR, which are usually they have deeper pockets, and you start with a larger drop. Then also the larger the drop is, the longer it usually takes to bind. And it's usually a drop like that can have a K of 10 to the 5, 10 to the 6. That's in terms of brute force, it's half millisecond to compute. But if you're doing the adaptive, maybe you can decrease 1 order of magnitude. Like maybe with 50 microseconds, you really see the binding, and you really can provide good estimates.
So that's 50 microseconds altogether, or per 2 seconds?
Altogether. So it's simulation like 100 nanoseconds or 50 nanoseconds, and then having 10%. That's usually. I would say 50 microseconds is a good starting point for getting good estimates for every system, and if the system is lower, maybe you need much more. So once we have that, I'm gonna show you the documentation of HTML so that you can play with different metrification procedures. So we have down here, as I mentioned, contact maps. But there are other ways to cluster our information. We can do RMSD contact maps. If we are talking about a protein, we can do distance contact maps. So at each trajectory, we look at the distances between the ligand and the protein. And there are many others, so I'm going to show you. This is the documentation of HTML. It's html.org. You can go now and try to see. And in here you have tutorials. So you can see there's also the ligand binding analysis tutorial. And in this case we're strips and benzamine, and you have all the explanation, how it works, a time scale. This, if you see, this one looks like a much converged time scale. It's a model we can trust, and it has separate carriers, and it's converged from the second nanosecond. This is a very good system. Very often we also get systems like the one I've shown you.